Well, guys, first thing I want to say is I made another mistake in the lab handout. Let me show you. This is our Lab 5 printout, the post-lab question number 6. A landscaping project requires topsoil to fill this volume. What is the total mass of soil required if bulk density equals 1.63 grams per cubic centimeter? The original handout that I posted did not have this value for bulk density. It didn't have any value for bulk density. So you will not be able to do this problem at all without this information. This is a pretty bad mistake. You're not gonna be able to do the problem without it. And thankfully I noticed it right after the Tuesday morning lab. So here on the Canvas page, there's gonna be an announcement about it soon, Lab 5 update or important news. You can scroll down to the Lab 5 module here where it says bulk density and porosity. This is where you got the handout in the first place. I left the old link up, the old version. I said, don't print. And then as of 11 a.m. on Tuesday, I had this new version, it's version 1.1. So that has a couple other updates. Most important is that it shows this 1.63 grams per cubic centimeter. So if you guys were confused by that already, I apologize. If you don't see this in time and get confused by it still in the future, I still apologize. It's still my fault. Hopefully you guys can work your way through it instead, and I communicated well enough that you know how to navigate that. So the reason you're here though, watching this video, is question 3 on the post lab, using Excel to create a graph or plot of our bulk density data. Where do you even start? Well, we can start in our exercise 2, bulk density core method data table. So you filled this all out now. This is my my raw sheet, but you've got your tin masses and your total mass that you collected in the lab. You subtracted these two to get the soil mass. You measured the volume of the core using the calipers. We'll assume the core stays constant for both of these, that all the cores have the same volume. Take the mass divided by the volume, mass over volume is density, and you get the soil bulk density. Hopefully your group noticed that the sample bags had labels, that they were supposed to go with one of these horizons, that you were supposed to keep the samples together in order. I believe most of you did. If you didn't, you're gonna find out about that pretty soon, I think, and hopefully you can work your way back to what it's supposed to be. Okay, so we've got 2 series, mollisol and andesol, horizons, depths, and then now bulk density is gonna be important. So let's go over to Excel. Here's our final product, what it's hopefully gonna look like. We've got our data over there and a scatter plot showing bulk density over profile depth is our title, bulk density on the x-axis, depth is on the y. Maybe that's the other way. We've got both series on the same plot with different symbols, different trend lines, and a legend. Okay, so this looks very nice. This is what we're going for. And here is how we get there. So starting with the blank sheet, first thing I'm gonna do is type in my name. Keep this a little organized. Let's say soil 206, lab 5, and then this is the bulk density graph. Okay, let's start off with the mollisol. We're just gonna type in our data, keep it a little organized like this. You can duplicate the whole data table if you want, starting with the tin ID and the empty mass, the total mass if you want, but the only data we're gonna really use is the horizon, not even that, the depth and the density is really all we need. So I'm gonna say just horizon, depth in centimeters, and density in grams per centimeter cubed. Okay, make that a little nicer. Our first horizon for the mollisol is AP, and then we have an A and an AB horizon. The depth measurements on each of those is 4, 16, and 32. This should all be the same for all of us. And now our density values. I'm gonna use some that I recorded from the past of 1.40, 1.24, and 1.34. Okay, I'm gonna do the same thing down here for the andesol. Horizon, depth, and density are just gonna be copied. Okay, but our horizons are different this time. We have an A horizon we have a BW and a BT. Okay, depth measurements are slightly different. 5 centimeters, 17 centimeters, and 32 centimeters. Density values that I'm using are 0.92 for the A horizon, 1.03 for the BW horizon, and 1.17 for the BT horizon. Okay, raw data is entered. Now we can go straight for the plot. I'm gonna insert a scatter plot. This is the best way to represent our data. I'm not gonna have any data selected because that, when I insert the plot, because that lets Excel choose the data for you. Do not let Excel choose data for you because it will be wrong every time. It will be wrong every time. Instead, we have this blank plot. I'm gonna right click and say select data. I'm gonna add a series here. The series name is gonna be mollisol. The X values that I want on the X axis is going to be the depth. Let's start with depth there. I'm just gonna click and drag over this box. And then the Y values are going to be density. Okay, and now I'm gonna add another series and I'm gonna call this one andesol. The X values are going to be depth as well. And the Y values are gonna be density, just the same. You can also type in what the series name is. That works too. By selecting a cell, it's more dynamic, so I can change the name if I want, and it'll also change in the plot. So I'm gonna leave that there, and I think we are good. Okay, so boom, we have a raw data plot. I'm gonna add a few of the elements that we need by using this green plus button there. We want an axis title, we want a chart title, we want a legend, and we want at least one trend line. Let's start with mollisol. And then I'm gonna say more options, add one for the andesol. Okay. So let's make this a little bit bigger now. We have more elements on this chart that take up space. What I'm gonna call this chart is something fairly simple. We'll go with bulk density over profile depth. This axis title is going to be bulk density. And we're going to include units because I will be grading for the units. The units are grams per centimeter cubed. Okay, bracket that. Change this one. This is going to be depth in centimeters. We just earned ourselves half a point, I think. Okay, now this really looks pretty good if we're going to submit in color. But if I'm going to print this out and staple it to my lab, or if I want to be considerate to potential colorblind audiences, I'm going to make this graph easier to read. So I'm going to change some of these symbols. Let's do the andesol first. So I'm just going to click on these data points. I'm going to make sure each one of those 3 is selected. It's highlighted. So now I'm going to start to format the data series. That's what it says in this formatting panel over here on the right. I want to change the marker type. So I'm just going to go over to the format and then the marker options. And let's use built-in, pick a new shape like triangles. Triangles look like a volcano to me. Andesols are the volcanic soils. So I'm pretty proud of this one, you know. And let's change the color too. Let's not leave it as regular orange. Fill on these marker types is going to be solid. Let's give it a university gold color. And also change the border to that same color. Okay, now we have 2 different series plotted. We have 2 different marker types for the series. Now the trend line looks pretty much the same. And if the yellow and the blue print as somewhat similar shades of gray on a printout, I don't want that to happen. So I've selected the line here. I'm on formatting the trend line in the formatting tab. And now I'm just going to change the dash type right here to, let's say, longer dashes. And then let's make that color match what we did before. Okay, those markers are a little bit hard to see, so I'm going to go back to them by selecting the data point. And let's increase the size of these markers. Okay, nice and big right there. We can leave the bulk density or the, let's see, the Molosol series as it is, or we can change the color to something like black and change the line color to also match black. So wait a second, I think we're done. We've got both. Let's check our problem text here. We've used Excel to create a graph of the exercise 2 data. Bulk density changes over soil profile depth. Both soil series are on one graph that features a title, axis labels, proper units, series labels, a trend line, and a legend. The legend includes the series labels, really. Okay, we're printing colored lines in grayscale, so we've changed the data point symbols to different shapes. We've also changed the trend line type, and we're ready to upload. So honestly, that's as simple as it should be, really. You can do something like this, drag the chart down below your data, go to File, Print, and change it to print a PDF. This looks pretty good. You can change the scaling to fit all the columns on one page, so you don't break the graph up over 2 different pages, which doesn't make much sense because you're just submitting it online anyway. This would be much easier for me to read, at least, if you care about my ease of grading. Just saying. But no, this looks really good. I could save this as a PDF and send it for uploading. So I would go back to the Canvas page, our home, go down to the Lab 5 module. We've got a Lab 5 upload option just for this very PDF or Excel plot. So you can click on this. It's worth this assignment technically is worth 0 points, but the whole question I believe was worth 8 points. So you're not required to upload anything here. There's also no due date, so it's not going to mark you late. This is here for your convenience. If you have a digital copy of the entire lab already, you can also upload it here. And yeah, if you just want to scan and submit your lab, this is a good place to do it too. So that's that, right? This is the plot. That's all it took. Excel just takes practice, honestly. It's really powerful. It's a really good skill to have. You can use this for so many things and not just your soils lab classes. So I really encourage you guys to not be afraid of it and just to take this as good practice for use in the future. Let's go back to the post lab here and see if I can talk about any of these, if any of you are still watching even. Post lab question number 1 deals with activity 1, exercise 1, the CLOD method. This is hopefully a fun activity. I do on the course evaluations at the end of the semester, I asked in the past students to kind of give me an idea of what some of their favorite labs were and what some of their least favorite labs were. And this one showed up quite a few times in the favorite labs one. People thought water displacement was pretty cool, but it's not a perfect method necessarily. There are many sources of error that could make our calculated values different from the true density. There's quite a few things we assume in doing the CLOD method. Number 1, probably biggest, is that the masses that are labeled on the tags actually are accurate. I think some students kind of keyed into that. They were testing, verifying just to make sure, and found some that were not quite accurate anymore. So the masses could be off. Another assumption that we make is that 1 milliliter or 1 cubic centimeter of water is equal to 1 gram of water is equal to 1 cubic centimeter. That depends on the temperature of the water, like the purity of the water, you could say. Probably another huge source of error would be if any part of the CLOD was not submerged underwater, or if the CLOD was touching the sides or the bottom of the beaker. That would introduce a lot of error. If you lost water, so if you took the CLODs, dunked them, took them out, and put the next CLOD in one after another, and didn't zero the scale in between reps at all, chances are you were losing 1 gram of 2 or water per CLOD that you dunk in. So by the end, after you've done all 8 or 9 CLODs, you might be off by 10 or 15 grams or so. I think one group caught onto that before it was too late and fixed the data. But there's plenty of options you have for sources of error there. Human error is unfortunately not going to cut it. I'll give you a point for attempting, but probably not much more than that. Number 2, using one of your horizon averages from exercise 1. So you did the 3 reps, take the average of them, you put that in this box. Just pick one of those horizons. You can tell me which one it was. and then calculate the porosity. So how do we know the volume of those pores, the air space inside of that clod? That's impossible to know directly, in my opinion. So we're going to infer it based on the bulk density. Thankfully, we already calculated that. So we'll take the bulk density, divide it by the particle density, and subtract that from 1. So you know this bulk density value, you've just calculated it. The particle density, like I said in the introduction, we can assume to be 2.65 grams per cubic centimeter. This is a productive struggle, I think, for a lot of students is, where do I get particle density? How do I calculate that? It's not something you have to calculate. It's something that you can assume to be 2.65. I think Robert and I have covered that one pretty well, but it's a good thing to keep in mind there. That's a pretty straightforward calculation. The answer is either going to be a decimal, so 0.4, 0.3, 0.5 or something, or a percent, 44, 50%, whatever you prefer. Okay, we did number 3. Number 4, in undisturbed soils, bulk density is usually lowest at the surface and increases with depth. Do the results in exercise 2 match this? They do not. Let's go back to our plot here. You can see that the andesol does. It starts off with low density and increases with depth. The mollisol data does not. The highest density is at the surface, and then it drops down, and then it returns back to the middle. So exercise 2 results do not match it. Well, they do for the andesol, the mollisol does not. What could be causing this difference? Let's take a look over here at our horizons again. We've got the andesol soil profile, probably from a forest. We've got an A horizon, BW, which means we have the color or the structure of a B horizon, but no other like interesting features. It's just the start of soil development, BW, and then BT means we've got accumulations of clay films right there. The mollisol starts off with an AP horizon, then we go down to A and then AB. So at the same depth as the B horizon, we're still in technically the A horizon. We've still got this dark brown, organic rich topsoil color with the A horizon. That's what that means. And AP on the surface. So we use this P subordinate distinction. We call it the lowercase letters. This subordinate distinction means some sort of artificial influence, probably from tillage or like pasture grazing or something, some compaction of the soil. It's impacting the soil profile so much or enough that we designate it in the official description in an AP horizon. So that's a pretty much dead giveaway that there's going to be some artificial influence is this AP layer. And that's likely from tillage or grazing that's increasing the compaction of this topsoil layer, but not necessarily what's below it. So in the top 4 centimeters, we've compacted that soil quite a bit from either tractor traffic or repeated use of the land in an agricultural system. And then the A and the AB horizons still retain their somewhat of natural density. That's the reason for the increase right there in the AP horizon at the surface. So some sort of artificial influence is increasing the compaction. Number 5, bulk density versus particle density. I think you've had some good repetition on this now. One of them is the volume of the total soil. So the mass of the solids divided by the total volume. The other one is mass of the soil solids divided by the volume of the solids. Okay, this landscaping project number 6 is a conversion problem really. If you multiply meters times meters times meters, you get cubic meters, which is the total volume you want to fill. I think that's about 14. Then, you know, the density of the soil is 1.60 grams per cubic centimeters. So you have cubic meters that you're going to fill with soil that we're measuring in grams per cubic centimeter. We have to convert the cubic centimeters to cubic meters. I know there's, let's see, so I'd write this as 1.63 grams divided by 1 centimeter cubed times 100 cubed centimeters cubed divided by 1 meter cubed. And then, so the centimeters cubed will cancel out. And then I also don't want the answer to be in grams because that number is going to be way too big. We're going to measure like 14 cubic meters of soil in grams. I don't think that's really going to work out. So multiply by 1,000 or divide by 1,000 grams under 1 kilogram. So the grams are now going to cancel out. And lastly, multiply by that 14 or so meters cubed volume. That'll cancel out the meters cubed. So all we're going to be left with is a mass, probably in kilograms. I think it's something really heavy. Soil is really heavy. 20,000 or so kilograms. Is that right? Maybe. It's you do the conversion, and that'll get you by far the most points. Let me know if you guys are having trouble with that. And extra credit opportunity here, that's for you guys to take a swing on. I think Robert's lecture content this week will be pretty helpful for that. And there's also a write-up in the post lab or in the supplemental. So what the impacts of tilling land repeatedly is, upon the first pass of tillage, it really loosens the soil and fluffs it up, so that might decrease the bulk density. But over long-term repeated passes of tillage, we can create those AP horizons. It generally increases the bulk density for reasons that I will leave to you guys to explain. So that is our Lab 5 handout, and that is one more look at the graph that I'm hoping to see from you guys. I would, you can have that printed out or uploaded. I'm interested to see what you guys come up with. And I'm glad to be giving you guys this opportunity to practice with Excel. Again, it's a really powerful tool, not worth being afraid of, in my opinion. So I wish you guys good luck. Reach out or post any questions on Canvas that you have about this lab, and I will see you guys next time.